Let's talk about calculating volumes using the washer method. When a solid of revolution has a cavity in the middle, and when I say cavity, this just means a hole, um, the slices used to approximate the volume are not discs, but washers, which are really like discs with a hole in the center. So if you think about it, you know, you can have like two concentric circles. This is what a washer looks like. Okay. So let's take a look at the washer method. And this time, instead of having just one function, we're going to have two functions. We're going to have f of x and g of x. And both of these need to be continuous, non-negative functions. Okay. And we need that f of x is going to be greater than or equal to g of x over some interval from a to b. So I want to draw a picture to help us really understand this situation. So let's create a y-axis over here like this. This is y-axis. Let's put an x-axis over here. Okay. And let's have one function, f of x, look like this. This is our f of x in blue. And let's have our g of x be some function like this in green, y equal to g of x. And then we need x value of a and an x value of b like this. And, this will be the left and right boundaries of the region that we care about. So we're going to call the region that we care about R. And this region R is bounded above by the graph of F. So we could see in this picture it's bounded above by the graph of F. It's bounded below by g of x, so it's the bottom of the region is g of x. It's bounded on the left by x equal to a, that's this vertical line. And it's bounded on the right by this vertical line, x equal to b. Okay, so let me shade this region R. So this region is the region that we're rotating it around, like so. And let me indicate the axis of rotation, rotating about the x-axis. So let me put a loop down there on the x-axis like this. All right. So what we want to do is we want to come up with a nice formula for how to calculate the volume of this solid of revolution. And I'm going to outline some steps for how we do these problems. The first step I would say is I would draw the region, like we've just done. The second step I would say is I would say chop up perpendicular, which I abbreviate with this symbol, to the axis of rotation. The third thing I would do is I would decide, is it a dx integral or a dy integral? And the way you're going to decide that is you're going to see where is the little bit of thickness. Okay. So in this particular example, you can see that my axis of rotation is the x-axis. So I'm going to chop up perpendicular to the axis of rotation like this. So this time I'll chop it up in red. So we're going to chop it up like this. We're going to go so on and so forth like this. And I hope that you can see that this little bit of thickness right there, that lies on the x-axis. So that's a dx type situation. All right. Once you've got that, all that information, then you can set it up as follows. So the fourth step I would say is set up your integral. And the way that we're going to set it up is it's going to be the integral. We've already picked out what our variable of integration is. That's going to be a dx type integral. Then you want to look at your region of integration and you want to say what's the smallest the x value can be. That's going to be a. What's the smallest the y value? I mean the largest the x value can be. And that's going to be b. So we're going to integrate from a to b. We are going to have pi times something squared minus pi times something else squared. Okay, so then the question is what goes inside those two parentheses? And the answer to that question is you can write your function values in. So in this case, it's going to be f of x is the bigger function and g of x is the smaller function. And this is because we're rotating about the x-axis in this particular case. If I wanted to describe the situation in general, I'd write this as r big, that is the bigger radius, and I call this guy r small, the smaller radius. Okay. Let's move on to the next page. I'm going to draw a similar picture for when we do it about the y-axis. So let's take a look at this washer method for volumes of solid about the y-axis. This picture is going to look pretty similar here. I'm going to draw a y-axis like this. I'm going to draw x-axis like this. We're going to have one function that's going to be our bigger function. So the bigger function is going to be to the right. So this would be x equal to u of y. My smaller function is going to be on the left. So this is going to be something like x equal to v of y. And I'm going to call my smaller y value c and my bigger y value d like this. So if I extend those horizontal lines out, then I hope you could see that you've created this region of integration right here. Or this is the region that we're rotating, I should say. I'm going to call this region Q. And I'm going to put a little loop around the y-axis to show that we're rotating about the y-axis. So, our steps, our first 3 steps are going to be exactly the same. I'm going to draw a picture. I'm going to chop up perpendicular to the axis of rotation. In this case, that means we're going to chop it up horizontally, like so. This means that in this case, our little bit of thickness lies on the y-axis. It's a dy type situation. And the only thing that really changes is, once you've picked out the fact that your integral is a dy integral, then the limits of integration will be the smallest y can be, in this case that's c, and the smallest that, the biggest that y can be, which is be d like this. So we're going to have pi times something squared minus pi times something else squared. In this case, the bigger function is the u of y, and the smaller function is the v of y. And I hope you can see why we call this r big. We call this guy r small. So again, the bigger radius is going to be the one that's on the right, and the smaller radius is going to be the one that's on the left. And those radii are given by the x values of our function, which in this case, the x value is the dependent variable. All right, folks, I will show an example of washers in the next video. Take care.